Can the law of gravity be used to calculate the free fall acceleration on Earth based on the Earth's mass of 5.97 times 10 to the 24 kilograms and Earth's radius of 6.37 times 10 to the 6 meters? And the amazing answer is yes. Based on the way gravity works, if I say, hey, here's an object that's, say, in free fall somewhere above Earth's surface, and of course, maybe I'll say, okay, here's Earth's surface, but we're going to look at this at a scale where that's curved. The way we can think about this in terms of the law of gravity is I would say this object is interacting gravitationally with the center of the Earth, which I'm imagining is just being some point far away, maybe a distance. In that sense, the distance between these two, right, that distance there really is going to be equal to the 6.37 times 10 to the 6 meters for Earth's radius. And we know that the mass of the Earth is given to us as 5.97 times 10 to the 24 kilograms. And in that sense, if we say, okay, well, what's the free body diagram? We're just talking about something that's falling here. We're talking about a force of gravity that is given to us by this universal law of gravity based on these input numbers. If we want to solve for the acceleration, though, because like, what's the picture for acceleration? I mean, I could, if I knew what the mass of the falling object was, I could just plug into here and find a force of gravity, right? But I wasn't given the mass of an object. We know that that actually shouldn't matter, but why is that true? Well, we have F equals ma, right? And if I put in force of gravity, the expression I have there for the net force, the two masses cancel. And oops, I forgot the over r squared here. Okay, let me fill that part in. That's very important not to skip. But the result is this lets us calculate what that acceleration is. So this gives us an expression of gm over r squared, which in this case, that m again is the Earth's mass. G, I think I'll just use 6.67 times 10 to the minus 11. That's good enough for 3 significant figures of accuracy. So let's see, that should be in newtons, meters squared per kilogram. Squared, I always got to think a little bit about that one, make sure I get it correct. We'll see if it balances out here. And then we got the 5.97 times 10 to the 24 kilogram. I have to write small because I'm running out of space. And then we're going to divide that by 6.37 times 10 to the 6 meters. Don't forget to square that. I've seen a lot of people, including myself, I've done it so many times, forgotten to square in Newton's law of gravity. It is an inverse square law, so it's very important to remember to do that. Anyways, lo and behold, if you plug all those numbers as I've kind of put them here into the calculator, you get like 9.81344, etc. But since we're at three figures of accuracy here, 9.81 is probably good enough. And I think we can probably trust, right, that this is, maybe you can go through it with a fine-tooth comb and check if it really works. But if I did and said everything correctly with the units, I think this should turn out to be acceleration in meters per second squared. So yeah, let's check that with our answer. And there it is. It says yes. It's basically got the same calculation we just did with the same units. So there it is.